Hello and welcome to Margaret and Graham's Math Podcast, Season 1. We're catching our stride. Isn't that right, Margaret?
That is exactly correct.
Thank you for tuning in. If you've tuned in, you know what we're about by now. We're about going over some math concepts, sort of having fun, having some sibling banter, and hoping that our listeners can relate in some way, or maybe you know us, maybe you don't know us, but hopefully you get something from this podcast. Today we've got a good one. Got something called related rates.
We're gonna completely switch topics from what we've been talking about so far. And instead of going over some basic geometry, we're just gonna jump right over to calculus and
Yep.
see how that takes us.
So I'd say we're going from about high school to, or maybe beginning of high school to end of high school, beginning of college.
Well, I mean, it depends on what math class you're taking.
Okay, not all of us, were in quadruple accelerated math in high
Right.
school.
All right. Try double accelerated, but let's calm down.
Ayo. This is calculus 1 material.
Yeah, this is Calc 1. So
Okay.
it's chill.
So for a lot of people, this is, the first math class you're taking in college. Or maybe you took it senior year in high school. But it's after pre-calc, and calculus, there's a lot you can do. A lot of real applications into useful technologies in the world. So let's jump right in. Let's get that whiteboard out and put Khan Academy out of business.
Hell yeah.
Shout out that boy Jason Liu, the comment. That was his idea.
Yeah, it was.
All right, so what's a related rate, Margaret?
Okay, so we're jumping into the concept of related rates. This is kind of already making the assumption that you do already have some basic differentiation skills under your belt. So if you don't know how to take derivatives, just real quick pause this video, go ahead, master differentiation, and then hop right back over real quick.
What's the derivative of x squared?
2x.
Cool.
That's all you need.
Get people into the mindset.
Yep. Cool. So related rates, conceptually, it's basically you're gonna imagine that kind of two processes are kind of happening at the same time. These processes are connected to one another, but you only know the rate at which one of these processes is occurring, and you're using that information to find out the rate at which the other process is occurring. Does that make sense so far, Graham?
Sounds simple enough.
Yeah, sounds simple enough. This actually was probably the thing I struggled most with throughout all of high school. But not to worry.
Sure.
I got it eventually.
For me, I feel like it was maybe talking to people, athletics.
Oh, talking to people, I just
Those I was pretty good at.
mastered. So I just sort of gave up on that one right off the bat. But here we go. Let's do an example. Graham, can you draw me please a horizontal line and then put a right triangle on top of it?
Sure. Oopsies. All right, here we go. It's gonna happen. I know it's gonna happen. And we're not waiting for my pencil.
No, it's looking great so far. Love it.
My pencil. Why isn't it working? Oopsies. You'll cut this out, Margaret.
Yes. No
I'm
problem.
trying to get my pencil to work.
Well, let me try.
No, I can do it.
Like that. That was what I was looking for. Cool.
Oh
Alrighty.
wait, I can do it. I can do it. I can do it. I can do it.
Okay,
Do it.
I'll let you label the hypotenuse, Graham. Make it 15
The question is it
units.
going to work for? Okay, all right, we're back. They don't know that we left. Margaret edits these, puts it back together, and what I'm going to do now is label the hypotenuse of this right triangle at 15.
Yeah, 15 units or 15 meters or 15 feet, whatever you want. It doesn't matter. The bottom of the triangle is going to be 10 gram, and the vertical portion is going to be 5√5.
Damn.
Cool. And I also want you to label the bottom as lowercase b, so base, and then the height as h, lowercase h.
Okay.
Yeah.
It's giving sailboat.
It is giving a little sailboat vibes. Cool. So, something to mention when it comes to related rates is that, as we said, you do already need to know about differentiation, and specifically you need to know and feel really comfortable with using the chain rule.
Ooh, now that is blast from the past.
Yeah.
I know that some of our listeners just felt something when you said chain rule, because
Yeah,
I felt
do
something.
a little review of the chain rule. Can you go in the top right corner and maybe do a little, say f of x equals parentheses x plus 2 parentheses squared. Let's just make it simple.
What's after this?
Squared. Yeah. All right, so now say we want to find f prime of x. This would be a case where we would use the chain rule.
Okay.
So f prime of x here would equal 2 parentheses x plus 2 parentheses. And then you would multiply it, you would multiply that by the derivative of
Yeah,
x to itself, which in this case
I
is
like that. It's just
so
one, right?
yeah, it's just one. So it's a
Oh, I
fairly
love
easy
that. It's been
example.
such a long time since I've done that because the derivative of 2 is 0, derivative of number just is 0, derivative of x is just 1. That's
Yeah.
clean. So
Yeah.
really this would be, would you rather have this written as 2x plus 4?
You
Most
could.
simplified form?
Well, yeah, I mean, I would maybe simplify it after I had written it as 2 times x plus 2, but 2 times x plus 2 is how I figured it out in the first place. So that would be what I would
Beautiful.
initially probably.
Beautiful. Now, as a student of number theory, what I like to do is a little one of those at the end.
Wow, Graham. I used to,
You like that?
I used to like to do the 3 dots in a triangle.
Sure. Well, that means therefore.
That does mean therefore. What did I draw at the end?
A little square. For those listening, you do a little
So,
square at the end of your math proof,
I
and
had
bada bing, bada
something.
boom.
Well, you can also write QED if you want. Stands for
Are you
something in
making things
Latin.
up again?
No, QED stands for something in Latin. It means like the end.
Moving on. So what we just looked at is the chain rule, where basically you've got
Yeah,
some parentheses.
basically, you imagine that whatever is inside the parentheses is just like just x or something. You take the derivative of that, then you multiply that whole thing by the derivative of just what's inside the parentheses. Cool. So erase all that or cross it out, please, Graham. Here we have a we can use the oh my goodness. Pythagorean theorem. Pythagorean theorem.
Sure.
B
That's
squared
that's a banger.
plus h squared is equal to 15 squared because we have a right triangle.
Okay. Love it. Love it. Oopsies. So you said
B squared.
now is that 10? So you want me to make that 100?
No, let's do B for now, please.
All right. B squared plus h squared
Equals 15 squared, which is 225.
units squared.
Yeah. So that's going to be 225.
And it's funny, I actually had a technical interview for an engineering job where they specifically messed up the units to try to see if I'd catch it. This is a good little gotcha.
Yeah,
You'd
you
think,
better
oh,
put
it's just
units squared
225 units. No, it's 225 units squared.
or square units. Yeah.
Sure. I've heard of
But
both ways.
it's easier to write units squared. Cool. So now, say in this problem, the information that you're given is that dB dt is equal to 1/4 feet per second.
Okay, what's dB/dt?
dB over dt, like the derivative of b with respect to time, I guess.
Sure. Okay.
Let's say that equals 1/4 feet per second. So
All right.
it is time because someone brought up a second.
Actually, that's the frequency.
Sweet.
All right.
And now
1/4 feet over a second.
what the problem wants us to solve, the question that we're given is solve for dH dt.
Mm-hmm.
So yeah, this is kind of what I was talking about at the beginning with related rates. We're given this rate of change of the base of the triangle here. And we want to find out the rate of change of the height of the triangle, because in this case the triangle is I guess shrinking because it's 1/4.
Interesting.
Yeah. Cool. So how do we want to go about solving this, Graham?
That's a great question. So let's think about what we're actually looking at here. We've got that 1/4 is dB over dt. So that's the difference of b over the difference of time. And that's what this area is, right?
That is B, yes.
Yeah, so I'm gonna let you lead how we're gonna approach this.
What I would do is I would first take notice of the fact, like, the formula that we're starting with is b squared plus h squared equals 225. The
Yep.
information we're given comes in the format of dB over dt. So I need to somehow change my initial equation into a form that has dB dt so I can actually use the information we're given. So
I'll stop you right there.
We're gonna
How
do the
about we
classic.
get b by itself, then take the derivative?
It really doesn't matter, Graham. I mean, you can, but like you can do it in the order doesn't matter.
Okay.
We're gonna do the classic that you are gonna do in a lot of problems is take the derivative of both sides, right? And the chain rule is gonna happen here. So you're
Beautiful.
gonna have 2b times dB dt plus 2h times dH dt is equal to 0. dB dt times dB dt plus 2h times dH dt
2h times dH dt
equals 0. And you see how that's using the chain rule? We're
Yeah, so what you're
derivative,
doing is you're doing
taking the derivative of b squared, and then you're multiplying it by the derivative of just b by itself.
b squared.
Which in this case we don't know super exactly because it's a word problem, I guess.
And why are we doing the chain rule? Are we doing the derivative of b squared plus h squared at the same time?
Yeah, in this case, this is an application of implicit differentiation, I think, if I'm remembering right. And
Sounds
it's
nice.
like, yeah, you would do the same thing if you were kind of dealing with x and y at the same time in one equation. You can only
Sure.
really do the kind of straightforward, easy differentiations when you just have the one independent variable.
Yeah, I'm with it. I'm with it for sure.
Yeah.
For sure. Okay, beautiful. So
Cool. So now we
now
get
what I'm thinking we do is we get dB dt by itself.
well, let's just plug stuff in and then to do the
Sure,
math.
we can do that. Why not? Let's do
Yeah.
a little bit.
2
Take
times
this,
10,
put it in there.
2 times 10 times 1/4 plus 2 times 5 root 5 times dH dt equals 0,
Sure,
and then
right.
solve for dH dt.
2 times 10 times 1 foot over 4 seconds plus 2 5 root 5 times dH dt is equal to 0. Wonderful.
Yeah.
I'm loving this. I hope everybody can see what's going on here. And then we simplify and solve for dH dt. Now we could do that out, but I think we all understand the algebra that's required at this point.
Yeah.
Basically, you just multiply out a little bit and then solve for that dH dt.
Yeah, so 20 divided by 4 is 5, and then you subtract on both sides, so you have a -5, and then you have 10 root 5 times dH dt is equal to -5. And then I run out of math I can do in my head.
Right, you can just divide that 10 away of the 10 root 5. So then it's root 5 d actually see that's what I'm saying. Why are we doing we don't need to do this. Everybody knows how to do algebra.
-1/2 root 5, right?
Write this.
Yeah, doesn't come out super pretty. That part doesn't matter. Really doesn't matter what the answer actually is. What matters is how we found the answer.
Yeah, we're just solving for dH dt.
Yeah,
and that's a great example. That's related rates.
Yeah, and now you might be thinking, I mean, whoa, it's not so often that I come across a right triangle that's randomly expanding or shrinking. And
I was thinking that, actually. I was thinking that last night.
And so what I have brought for us all today is a much more relevant word problem. So let me start a new page here.
Fresh whiteboard.
And
there's something about a fresh whiteboard, the opportunity it presents. You step into that math class. If you're in college, maybe it's a chalkboard.
Maybe.
What might those numbers mean?
In this case, they're going to be talking about a balloon. And now once again, we're going to kind of suspend reality for a little bit because our balloon in this word problem is going to be perfectly spherical, which, as we all know, I at least have never seen a perfectly spherical balloon.
My balloon guy does that. He's great.
You got to give me his contact info after this recording then, yeah?
It's the same guy who makes the ellipsoid balloons. He's a pro.
Sounds like it.
Yeah.
Pretty excited.
But if you're not near Venice Beach, Los Angeles, you probably have not seen a perfectly spherical balloon. But imagine one.
Yeah. So imagine a perfectly spherical balloon. And in this case, air is being pumped into this balloon, right? At a rate of 5 centimeters cubed per minute.
Goddamn.
So you can write that down, Graham. 5 cubic centimeters per minute. So obviously we're with volume here, the centimeters are cubed.
Okay.
And that, I'm not sure if you guys know, but that's a pretty typical rate for balloon inflation.
Sure.
Specifically with perfectly spherical balloons. So
yep.
Don't question that number too much, I would say. Anyways, now what we're going to do is answer the following question. What is the rate at which the radius of the balloon is increasing in diameter at the exact instant when the diameter of the balloon is 20 centimeters? So what you have to be thinking about here is that the balloon starts out really small, it eventually gets really big. Throughout this whole process, the rate at which the diameter only of the balloon is growing, that rate is changing. So we are going to only be looking at what the rate is at that one specific instant.
This is a great question.
This is, yeah, and it's something that comes up frequently, I would say. So
I mean, it absolutely could come up. Different type of engineering and device design considerations. In medical devices, if you're working on like a stent or something.
No, it is a fairly
or a sheath, something that holds a vein open.
In some ways of just two things are happening at the same time and you're given one rate and you need to find out the other.
Is this like the trolley cart problem?
What trolley cart problem?
Where, you've got a lever and it's a philosophy. Never mind.
All right, no, not that problem. How is that even remotely related? What philosophical question is involved in inflating this balloon?
You're taking the last breath of air from a patient who needs pure oxygen, but instead of keeping that one patient alive, you can, keep 12 babies alive. But you have to take the oxygen away.
This is not a morality class. This is not a morality.
I digress. We digress.
This is
expanding. We want to know at what rate is that diameter increasing? Right when it hits 20 centimeters.
So here's where we're going to start. We are going to start with the equation for the volume of a sphere.
Sure.
Luckily, we just went over that last class. Volume is equal to 4/3 pi r cubed. And this is why it's really important that it was a perfect sphere balloon, because otherwise we would have to invent a new formula for a non-perfect shape, and that would be too hard. Cool. All right, related rates problem. So let's derive both sides.
At first, I was scared. I was petrified. I will derive
the number of calculus puns. It's just so many.
So we're going to say dv. Come on, pencil.
Make sure it's a capital V.
dv over, are we doing time?
dt? Yeah, dt.
It's almost always time.
Minutes, yeah, it's normally t. equals
equal to
4 pi r squared times dr dt.
good job, Margaret.
The threes cancel out, folks.
dv dt.
dr dt. Graham, that's the whole point.
Oh, silly. And that's just a lesson. I mean, you can be a guy like me who's literally hosting a math podcast and still make a mistake, and that's okay.
That's true. That is true.
All right, so we've got dv dt is equal to 4 pi r squared dr dt.
Yeah. Now, simple situation before us of just plug in the numbers and do the algebra. So we know we're looking at the exact instant when the radius, or sorry, when the diameter of the balloon is 20, which means the radius is going to be 10. So remember to keep that in mind. So we can plug in 10 for r. So it's going to be equals 4 pi times 10 squared dr dt. And then on the other side, we're going to have our rate that we're given, which is 5 centimeters cubed per minute. Yep, now we just have to solve for dr dt.
Beautiful.
Which looks like it's going to be 5.
Now what we're doing, this is like pro level math, where
this is not pro level math.
I'm literally just going to do dr dt is equal to the value without showing how I got there. But put a message in the comments if you have any questions, and I can explain it. Let's do this thing. Basically,
I think it's going to be 5 divided by 400 pi.
It's going to be a 2. It's going to be a 2 pi.
Sorry, where did you get that
from?
No.
We've got, okay.
Why would it not be 5 divided by 400 pi?
5 divided by 400, yeah. Yeah.
5 divided by 400
But what's 5 divided by 400? Come on, let's simplify that. 20 times 4, 80. So it's going to be pi.
No, the way you do it is you just
centimeters
400 divided by 5
80.
Is 80. Yeah. Graham, the pi's on the bottom, on the denominator.
Oh! There we go again. Then you can literally be hosting a math podcast and still make mistakes. And in all seriousness, that's why we don't do that. That's why you write out each step.
Oh, the other thing, this is a key thing to note because we forgot our units. Graham, where you put the 10 squared, it's a radius, so that's 10 units squared. So when we divide everything out, we're going to just end up with regular centimeters, not centimeters cubed.
Oh, okay. So we're going to say that radius was centimeters squared. So I'm going to take that out, make that a 1. So dr over dt is equal to
1 centimeter over 80 pi minute.
1 over 80 pi min.
Yeah, 1 centimeter. Yeah, I believe that's it.
Over 80 pi min.
Yeah.
And like always, we're going to have an anonymous report line, an anonymous tip line. If you think that we got any of the math wrong, you
Which
can
is a very,
tell on us.
Very real possibility. Well, yeah, don't be afraid to let us know. I did out the math at one point and I got 0.003978, either 9 or 7. I can't read my own writing. So yeah. That looks
the first rule of math. First rule of math, no calculators allowed.
That is not.
What did you say you got? 0.0039?
Yeah. 7.
Okay.
8.
Yeah.
9.
Yeah. Yeah, we're good. I'm just kidding. I used a calculator. Okay. Beautiful. What a great related rate. And that's so cool. Now I know.
Now you guys all know
Oh,
what to
okay.
do the next
One,
time you're walking by a balloon creator on the street.
you've got a flow rate like that of 5 cubic centimeters worth of air.
Per minute.
You know that that balloon is expanding at 1/80 pi centimeters per minute. And, if you remember your algebra, I believe, you can convert that to seconds. So you can think, oh, how many centimeters is this going to expand in 1 second?
True. Yeah, that was from chemistry, right? Unit dimensional analysis. What's it called? When you just
You
change
know,
units, you multiply
as as
by 60
as some
seconds from 60 seconds. No, you divide by 1 minute per 60 seconds. So the minutes cross each
as
other.
somebody who minored in physics as well, I'd say that it was physics. But ask a chemist, and she'll say that it was chemistry.
Fair enough. Fair enough. I don't know. I'm trying to think of anything huge and life-changing to kind of drop at the end of this episode, but I don't know. I don't know what to say.
Let me ask you a question, Margaret.
Do it.
The last time you saw math in your normal life, where you're,
Oh,
walking on the street, maybe you're at the dentist, maybe you're getting groceries, maybe you're getting your car worked on, and you looked at something and you thought, hey,
real life, not work, not school, not anything like that. That's the question.
that's life too. It could be wherever, but no, it's not. Oh, boss man just gave me this integral he needs by the
Yeah.
end of the day. It's not one of those. You have to answer immediately.
Well, Dad gave me this book for my birthday.
Sure.
It's
My
called
goodness.
Oliver Burns' Elements of Euclid.
For
So
those of you who don't
basically,
know, Euclid was a mathematician. There's
a long
Euclidean.
time ago, ancient Greece, I believe. So basically, he was super long ago. Then this guy, Oliver Byrne, was like, yo, I'll rewrite Euclid for the modern era. But that was still like 150, 200 years ago. So then this other guy, I don't even know, I guess he wrote this book, was like, oh, I'll update Oliver Burns' book for the modern era. And now here we are today. So yeah, it's about geometry.
Wonderful.
Yeah. What would you say, Graham, as the answer to that question?
Well, let's see. Um, where I live in the city of Angels, Los Angeles, sometimes I see a train go by, and sometimes I think back to my Newtonian mechanics physics class, where we talked about reference frames. And, there's a lot of math that goes into physics. Uh, Mathematicians and physicians will battle until the end of time over.
Physicists, Graham. Physicians are doctors.
That's hilarious. I did know that. No. Physicians also care about this, Margaret. The amount of dermatologists I've run into who have a horse in this race, it would blow your mind.
One?
Um, many. When I go out on the street, I see troves of dermatologists talking about math versus physics. Anyways, I think about reference frames on a train. I'm like, if I'm on a train and I'm in that reference frame and, I toss a ball up, is the ball moving left to right? It's relative to the outside. But relative to me in that reference frame, no, it's not. And I think, oh, what different types of calculations could I do? A little bit of D equals RT. And then if I really want to get spicy, get into some acceleration. You can use some integrals to do some velocity. Go back and forth from acceleration to velocity, all of that jazz. I think about when I see the subway. Now, do I think very in depth? No, but I know that those concepts are there if I wanted to, kind of pry open the world of math and physics and in the physical world that surrounds us.
That's beautiful, Graham. Beautiful.
Thank you, dear sister.
Anytime. All right. If you have any topic requests for our next episode, drop us a comment.
I'm thinking we can make this sort of the way we end episodes is we talk about where we saw math in the real world since our last recording, and I'll keep my eye out. I'll be
Well,
looking
now
for it
that I know, I will keep a sharp eye peeled.
Field eye. On
Yeah.
that pleasant thought, thank you for tuning in to the Graham and Margaret podcast.
Thank you. Thank you.
I believe it's the #1 math podcast currently streaming. I haven't looked at the charts
That sounds
recently.
right. I have not looked at any data, but I think it sounds right.
And also, we'll be hiring a summer intern. So if anybody would like to apply, it'll look very good on your resume.
Oh, great on the resume. This is an unpaid position, just as a heads up.
Right, but who can put a price on the value of this experience?
Exactly. See you later.
Ciao. Have fun.